We are looking at Flash-GRPO, efficient alignment for video diffusion via one-step policy optimization. And I mean, if you were trying to align a massive, like 14 billion parameter video model using reinforcement learning, you already know the nightmare.
Oh, it is absolutely brutal.
Right, you are burning literally hundreds of GPU days just to backpropagate through full denoising trajectories. You might have tried cheating this with naive sliding window subsampling, but you probably just watched your optimization stability completely collapse.
Yeah, it just falls apart.
So today, we are breaking down how Flash-GRPO completely changes the math. It introduces a one-step training framework that delivers a 6x training acceleration, and it actually matches or even exceeds full trajectory performance.
Which is a huge claim.
It pulls this off by solving two fundamental mathematical bottlenecks. First, there's iso-temporal grouping to eliminate timestep-confounded reward variance. And second, temporal gradient rectification to neutralize the time-dependent gradient scaling factors that have been quietly sabotaging your parameter updates.
And that 6x acceleration, I mean, that isn't just a nice-to-have benchmark. It is literally the difference between a project shipping and a project is bankrupting your compute budget.
Exactly.
To really grasp what Flash-GRPO accomplishes, you have to look at why those baseline efficiency methods fail so catastrophically in the real world. When we talk about aligning modern video models...
Like getting them to stick to prompts or not break physics.
Right, yeah, getting them to adhere strictly to your prompts, respect physical laws, or just, produce aesthetically pleasing frames without morphing into some eldritch horror. We are usually relying on group relative policy optimization, or GRPO.
Yep.
Specifically, GRPO adapted for flow matching architectures. You've probably seen this implemented in frameworks like Flow-GRPO or Dance-GRPO.
Right. I mean, those are pretty much the standard tools right now for dense supervision.
Exactly. But the standard paradigm demands that you compute gradients over the full trajectory for every single time step in the generation process. So say you are generating a 64-frame video.
Right. Okay. Standard length.
And your flow matching process takes, let's say, 50 integration steps. You are storing activation states and backpropagating through that entire unrolled computation graph.
Oh, man.
Yeah. For a 14 billion parameter model, the memory consumption is just absolutely prohibitive. You are forced to use microscopic batch sizes, incredibly heavy gradient checkpointing, and your training throughput just slows to an absolute crawl.
It's basically impossible.
It really makes iterating on alignment almost impossible for anyone without a dedicated data center at their disposal.
It's like trying to correct a type word on page 500 of a manuscript. But the rules of the system force you to rewrite pages 1 through 499 from scratch.
By hand.
By hand. Just to see if your typo fix actually worked. Doing that for every single parameter update is just computationally bankrupting. Which is why researchers started trying to find a shortcut in the first place, right?
That's exactly right. The community introduced methods like Flow-GRPO Fast and Mixed-GRPO to try and bypass that exact memory bottleneck. Right. And the core premise they use is sliding window subsampling.
Okay, how does that work?
It sounds entirely logical on paper. Instead of computing gradients for the entire denoising trajectory, you just sample a small consecutive subset of time steps.
So instead of all 50 steps, you do, what, a few of them?
Yeah, say 3 or 4 steps out of the 50. And you only compute gradients for that specific little chunk.
I mean, that makes sense. You save massive amounts of VRAM, you speed up the iteration time, and you theoretically still teach the model how to denoise.
Theoretically, yes. But as the Flash-GRPO paper details empirically, it comes with a fatal flaw. Naive subsampling just severely compromises the optimization landscape.
How so?
Well, when you look at the training curves for these one-step or fast versions, they exhibit massive instability. They completely fail to reach the performance ceiling that you get with full trajectory training.
Wait, really? They just plateau?
Or worse, you end up with this brutal trade-off where, sure, you save compute, but your model's alignment quality plateaus at a mediocre level, or the model just flat-out collapses mid-training.
Okay. Let's pause and figure this out, because intuitively that feels kind of wrong.
How do you mean?
If we just randomly sample one step to optimize, as these fast methods do, why does the model's performance physically collapse? Shouldn't it just, learn the alignment 6 times slower?
You would think so, right?
Yeah, because if you were only getting 1/6 of the gradient information per pass, why doesn't it just take longer to get to the exact same good result? Why does the reward curve literally fall off a cliff?
Because you aren't just learning slower, you're actually injecting mathematical chaos into the reward signal itself. You are giving the optimizer completely bad directions.
Oh, I see.
And this brings us to the first of the two root causes identified by the Flash-GRPO team. They call it timestep-confounded advantage estimation.
That is a mouthful. Unpack that for us.
Let's look at how naive single-step GRPO handles a prompt group during training. For a given prompt, say a dog surfing, you generate a group of rollouts, maybe 8 different video generations, to calculate your advantage.
Right.
The advantage is just a metric of how much better or worse a specific generation is compared to the baseline average of that group of 8.
Okay, yeah, that is standard GRPO. You reward the ones that look better than the average, and you heavily penalize the ones that look worse.
Exactly. But in the naive subsampling setup, each of those 8 rollouts within that group is assigned an independent, random time step for optimization.
Wait, hang on. So within one prompt group, for the exact same prompt, some rollouts are being evaluated at early stages where the frame is mostly pure noise.
Yes.
And others are being evaluated at the very end of the trajectory where the video is almost fully formed.
Precisely. And that introduces a massive confounding variable, because the reward variance you are trying to measure with GRPO is supposed to strictly reflect the quality of the policy's generation.
Like, did the model actually follow the prompt well?
Right. But because the time steps are mixed within the group, the baseline average becomes this polluted mixture of rewards from varying noise levels. You are entirely entangling the policy's actual performance with the inherent difficulty of the noise level at that specific time step. Yeah, the advantage estimates become wildly unstable because you aren't comparing apples to apples anymore.
Oh, I see. It's like grading a class where half the students are forced to take advanced calculus and the other half are taking basic addition.
Yes, exactly.
And you are trying to grade them all in the exact same curve. The grades don't tell you who the smartest student is. They just tell you who got the easiest test.
That's a perfect way to put it.
If a generation gets a low reward, the optimizer literally doesn't know if it's because the model generated a bad video or if it just happened to be sampled at a time step that is inherently way harder to denoise.
Right, the signal is totally garbled.
So how does Flash-GRPO actually fix this grading curve?
Through a mechanism they call iso-temporal grouping, or ITG. It enforces a very strict rule. For a given prompt, all rollouts in the advantage group must share the exact same time step.
Okay, so if rollout 1 is evaluated at time step, say t equals 0.7.
Then rollouts 2 through 8 for that prompt must also be evaluated at t equals 0.7. The only thing that varies between the rollouts is the initial Gaussian noise.
Interesting.
By enforcing identical time steps within the group, you completely factorize the advantage computation. You totally decouple the policy-induced variance from the time step-induced variance. So now the relative performance comparisons are happening under identical denoising conditions.
That is super clever. But hold on. If we are restricting an entire prompt group to just one single time step, don't we completely lose the temporal diversity required to actually train the full diffusion process?
That's the immediate concern, yeah.
Because the model needs to learn how to align the video across the whole trajectory, right? From pure noise down to crystal clear video. Not just at one arbitrary point. If we lock a prompt to one time step, aren't we just blind to the rest of the generation?
That's a great catch, and it's where the global batch design comes in to save the day. Temporal diversity is fully preserved, but it's handled through stratified sampling across the global batch, not within the individual local prompt group.
Oh, okay. Explain that.
Think about your overall training batch. If you have a batch of, say, 32 different prompts, each of those 32 groups is assigned a different time step drawn from a uniform distribution.
I see.
So prompt group A is entirely at t equals 0.1, prompt group B is entirely at t equals 0.9, and so on. The model as a whole is still updating its weights across the entire temporal trajectory during every single training step.
Right.
But the crucial advantage estimation, the RL reward signal, remains mathematically pure and unconfounded within each local group.
Okay, that makes perfect sense from a batching perspective. But there is a mechanical question here that I want to clear up for the engineers tuning in.
Sure, go for it.
Standard flow matching, which models like 1.2.1 use, relies on a deterministic ordinary differential equation, an ODE, for the forward process, right? It's deterministic.
Yes, it is.
But reinforcement learning fundamentally requires stochastic exploration. The model needs to try different actions to see what yields a better reward. So how are they actually sampling this single time step if the underlying trajectory is just an ODE?
This is honestly one of the most elegant parts of the paper. They utilize an ODE to SDE transition mechanism within the generation pass itself.
Okay, how does that work?
Let's walk through the forward pass for a prompt group. For all the steps from pure noise down to the chosen target time step, They integrate using the standard deterministic ODE solver. It's fast, it's very stable.
Makes sense.
But exactly at the target time step chosen for that group, the model momentarily switches to stochastic SDE sampling.
Oh, wow.
Yeah, specifically adding a controlled noise injection based on the Euler-Maruyama discretization.
Ah, so it intentionally injects a bit of randomness right at the exact moment we want to calculate the gradient.
Exactly. This SDE step provides the action exploration needed for the GRPO algorithm to actually function, and it allows for the policy gradient computation.
And then what happens after that step?
Once that single stochastic step is computed, the model switches right back to the deterministic ODE solver for all the remaining time steps down to t equals 0.
That's brilliant.
It really is. This hybrid approach is brilliant because the ODE steps maintain high-quality, stable generation, which ensures the final video is coherent and your reward model can give it an accurate score. Meanwhile, that single SDE step gives you the mathematical hook you need to do your policy optimization without having to backpropagate through the entire chain.
Okay, so isotemporal grouping fixes the grading curve. We are finally getting an accurate, unpolluted reward signal.
Exactly.
But, and this is a big but, even with a perfect reward, if I look at the training charts for the baseline methods in the paper, the models still collapse at around 300 GPU hours. The reward signal wasn't the only thing breaking, was it? Something is going wrong with the actual parameter updates themselves.
Yes, and this is where the paper gets profoundly mathematically rigorous and where we uncover the second massive bottleneck. The second root cause of instability is the intrinsic structure of the policy gradient itself under this specific flow matching framework.
Okay.
It comes down to a phenomenon the authors term time-dependent gradient scale heterogeneity.
Gradient scale heterogeneity, meaning like the size of the gradients is changing depending on time.
Precisely. When you derive the explicit policy gradient for the reverse generation process, you are dealing with a Gaussian transition kernel. And this kernel is induced by that Euler-Maruyama discretization of the reverse time SDE we just talked about.
Wait, if Euler-Maruyama is just the standard math we use to map the noise backwards in continuous time, why is it destroying our gradient? Are we accidentally scaling the model's weight updates based on how much noise is left in the frame?
That is exactly what is happening, and it is completely hidden in the math of the score function.
You're kidding.
Nope. Without getting completely bogged down in the algebra on audio, we need to look at what happens when you expand the gradient of the log probability for the policy update.
Okay, stick with me here.
Because of the SDE formulation, the formula includes a drift correction term and a diffusion coefficient. These introduce specific scaling factors based on two things: the current time step, t, and the current noise level, which we call sigma t. When you carry the math all the way through to calculate the final policy gradient, you find that the gradient is intrinsically multiplied by a time-dependent scaling factor, which the authors denote as lambda of t.
Okay, so every single time the optimizer takes a step, the size of that step is being multiplied by this hidden lambda of t variable.
Exactly.
What is driving the size of lambda of t?
It's driven primarily by the ratio between the time step size and the noise level, sigma t. And if you think about the physics of the diffusion trajectory, the noise level sigma t and the time t vary wildly from the beginning to the end of the generation.
Right. I mean, at the beginning of the reverse process, the frame is almost pure static, so the noise level is at its absolute maximum. And at the end, the noise is practically zero.
Exactly. And because they vary so drastically, this mathematical lambda of t factor fluctuates by literal orders of magnitude depending on where you are in the trajectory.
Wow.
This is a massive structural pathology for your optimizer. If you are training different prompts in your global batch at different time steps, which we just established we have to do for temporal diversity,
All right.
this lambda of tit acts as an implicit heterogeneous weighting factor on your parameter updates. The gradient magnitudes are just vastly inconsistent.
It's like you have a massive audio mixing board in a studio, but the physical slider for the bass channel is fundamentally broken, and it acts 100 times more sensitive than the treble slider.
That's a great analogy.
Even if you just want to do a perfectly balanced mix, the slightest millimeter of touch to the bass slider just blows out the studio speakers, while you have to slam the treble slider all the way up just to even hear it.
That is exactly it.
Right.
Mathematically, because of lambda of fits, the early time steps, the base in your analogy, completely dominate the parameter updates. They send massive gradient norms into the optimizer, regardless of how important they actually are to the final generation quality or the reward signal.
This raises a really critical point for anyone who has watched a run fail. If lambda of tat causes such an extreme imbalance, does that mean unrectified baseline models like Flash-GRPO fast were effectively ignoring the later stages of diffusion entirely? Is this uncalibrated variance what leads to that catastrophic reward collapse we see in the charts?
That is precisely what is happening. If you've ever had a cluster running for weeks and it just suddenly dies, this uncalibrated variance in the gradient scales is the theoretical root cause of your optimization instability.
That is wild to finally have an answer for.
It really is. If you look at the empirical data in the paper, unrectified baseline models suffer a severe collapse in the training reward curve right around 300 to 400 GPU hours. The gradient norms experience wild fluctuations because the early time steps are inducing massive destabilizing parameter updates.
And I assume those updates just wreck the model.
Yeah, these massive updates essentially overwrite all the nuanced fine-grained learning happening at the later time steps. It just destroys the alignment. So how does Flash-GRPO's temporal gradient rectification, or TGR, fix the sliders on our mixing board? TGR simply recalibrates the board mathematically so that 1 millimeter of movement means the exact same thing across all frequencies. Flash-GRPO explicitly normalizes this imbalance by rescaling the gradient by the inverse of that scaling factor, so 1 over lambda of t.
Okay, so it just cancels it out.
Exactly. By analytically dividing out that exact time-dependent bias, it forces the gradient scale to unity for all time steps.
That is incredibly elegant.
It completely neutralizes the discretization-induced bias, ensuring that every time step, whether it's pure noise or almost a finished video, contributes uniformly to the parameter update based on its actual reward, not its noise ratio.
Which brings us to the empirical validation and, frankly, the real-world engineering value of this paper. I really want to emphasize this for the ML engineers tuning in.
Yeah, the practical application here is huge.
Suffering a catastrophic model collapse at 300 or 400 GPU hours on a 14 billion parameter model isn't just an interesting academic curiosity to write a paper about. It is an incredibly expensive failure.
Very expensive.
You are talking about tens of thousands of dollars in compute budgets being set on fire just because your gradient's destabilized. The fact that Flash-GRPO eliminates this efficiency quality trade-off is a massive financial and temporal win for AI teams. Let's look at how they prove this actually scales in practice.
Well, they rigorously validated the Flash-GRPO framework on the WAN 2.1 family of flow matching models. They didn't just test it on some tiny toy model either. They specifically looked at both the 1.3 billion and the massive 14 billion parameter variance.
And the results.
The primary headline metric, as you mentioned in the beginning, is that 6x acceleration in training cost compared to the full trajectory Flash-GRPO baseline. But crucially, it maintains absolute stability throughout the entire run.
And what do the actual reward metrics look like on the held-out validation sets? Does the model actually look better to human evaluators?
Yes, it does. They measured this using the HPSV3 reward curve, which is a standard metric for measuring human preference alignment. Basically, how well the generated video aligns with what a human actually wanted to see from the prompt.
Gotcha.
Flash-GRPO achieves consistent, monotonic improvement throughout the training run. On the held-out evaluation set, it hits a reward score of roughly 5.35.
Which is high.
Very high. Contrast that with the Fast1 baseline, which uses the naive subsampling we discussed earlier. That maxes out significantly lower, around 4.9, before suffering from that severe instability and collapsing.
Ouch.
Furthermore, Flash-GRPO actually outperforms the full trajectory training in overall alignment quality under an equivalent computational budget, simply because it can process so many more iterations stably in the exact same amount of time.
But they aren't just chasing a specific reward scalar, right?
Yeah.
Because we all know that sometimes when you aggressively optimize a model for RL alignment, you end up destroying the backbone model's foundational generative diversity.
Right. It gets good at the test, but bad at the actual job.
Exactly. It gets really good at scoring high on a benchmark, but the videos look stiff or totally unnatural. Did they test the general video quality?
Yes, that's known as the alignment tax, and it's a huge problem in video diffusion. But Flash-GRPO avoids this trap. They ran comprehensive tests across the vBench metrics, specifically looking at aesthetic quality and motion quality. Yeah. Across the board, Flash-GRPO shows strong improvements without degrading the base model at all.
Talk to me about the motion quality specifically, because if we are tweaking how gradients update across time, I imagine temporal coherence could easily break.
Exactly, and that's exactly what happens to the baselines. On motion quality, which assesses temporal coherence and dynamic consistency, so making sure an object moves naturally from frame to frame, the baseline Flash-GRPO Fast 1 exhibits wild instability patterns.
The gradients just tear the video apart.
Yeah, the unrectified gradients totally wreck the temporal dynamics. But Flash-GRPO maintains stable, continuous improvement. It reaches a final score of approximately negative 0.28 compared to a much worse negative 0.34 for the baseline.
That is a significant delta.
It is. This confirms that decoupling the time step difficulty via isotemporal grouping and rectifying the gradients via TGR doesn't just make the math cleaner on a chalkboard. It translates directly to noticeably better temporal dynamics and visual quality without sacrificing the model's core generative capabilities.
Okay, let's zoom out and synthesize what this all actually means for the field.
Oh.
The bottleneck of single-step video RL alignment, which seemed like an unsolvable trade-off between compute costs and model stability, has been fundamentally solved by diagnosing and fixing two hidden biases.
Two very stealthy biases.
Right. First, by implementing isotemporal grouping, we decouple the policy's actual generation performance from the inherent difficulty of the noise level at any given step. This ensures our advantage estimation, our grading curve, is mathematically pure. Second, by implementing temporal gradient rectification, we mathematically neutralize the bias introduced by the SDE discretization. This ensures that every time step gets an equal, balanced vote in the parameter update, preventing those early, noisy time steps from blowing out our gradients.
It truly is a masterclass in AI research. It's about diagnosing exactly why a seemingly logical efficiency, hack-naive sliding window subsampling fails in practice, and then using rigorous mathematical analysis to build a robust, scalable alternative from the ground up.
It's beautiful work.
It really takes massive video model alignment from a compute-prohibitive luxury reserved for megacore and turns it into a highly scalable engineering reality for the rest of the industry.
And that leaves us with a massive thread to pull for the future. We've just seen that single-step policy optimization can be fundamentally stabilized for video diffusion by correcting these temporal and mathematical noise biases. But diffusion architectures are practically eating the world right now.
Oh, absolutely. They're everywhere.
So what if we applied these exact temporal debiasing techniques, isotemporal grouping and gradient rectification, to other complex modalities that rely on continuous noise trajectories?
Oh, that's an interesting thought.
Right. Imagine applying this exact math to 3D asset generation or even raw audio diffusion models. Could this specific combination of decoupling the reward and rectifying the gradient scale be the universal key to cheap, perfectly stable RL alignment across all diffusion architectures?
I wouldn't be surprised if we see papers attempting exactly that in the next few months.
If you are running an ML engineering team, this is exactly the kind of architecture you should be testing in your pipelines right now. Thanks for tuning into this breakdown. Keep experimenting, keep optimizing, and we will catch you next time on the AI Paper Slop YouTube series.